Thank you very much, Claire. Kia ora, everyone. As Claire mentioned, I'm Dr. John O'Sullivan. I'm the co-director of the Geothermal Institute at the University of Auckland in New Zealand, and it's a real pleasure to be here today to talk about advanced modelling for resource assessment during the exploration stage. At the stage that we are here in Taiwan, when we're looking at developing new resources, a key part of that is trying to understand, what is the scale, what's the style of the development that we're going to be proposing, what kind of return on investment would you expect? And one of the important things is understanding maybe some of what is the worst case, what are the failure modes, what should we be looking out for when we're trying to develop these geothermal systems. And we need to make these decisions using our best evidence, not just guessing. And we have some industry standard tools that I'll talk about as well that I've been using for a long time. But what I'm going to show you today is how we use uncertainty quantification with advanced reservoir modeling to give us better evidence for making these decisions. And this is pretty new technology. I'll talk this through. We first presented this in 2022 at Stanford Geothermal Workshop, and I'll talk through the projects, but we've applied this successfully to a number of commercial and research projects now. And one of the reasons that we can do this is we now have the capability of running reservoir models in the cloud. We've been partnering with AWS and Microsoft Azure, but particularly AWS. And, Taiwan is a very technically advanced society, and so you'd be very familiar with this, but the web-based, cloud-based computing services mean that we can run ensembles of reservoir models very quickly and very cheaply without needing a lot of expensive IT equipment in every company. And so just as a quick comparison, a standard production scale reservoir model that used to take 8 hours to run on existing technology developed at Berkeley and at the University of Auckland now runs in about 3 minutes and costs less than $1 to run. So this is an absolute game changer, and you can run 10,000 models for $1 each, all at the same time, and get the results back in 3 minutes. And that is an absolute game changer for how we think about it. This is something that oil and gas have had access to this technology for longer, and so this won't be unfamiliar to people coming from oil and gas, but for geothermal, this is brand new technology and really is going to change the way we do our decision making. And these are just some examples of, these are projects in South America and in New Zealand and in Indonesia, where again, we're just looking at orders of magnitudes faster, 12 hours to 17 minutes for these large scale models. And the key thing, one of the things that we thought when we developed this new technology was that we would run higher and higher fidelity models. And that is, we have been doing some of that, but what we found, in fact, the real value wasn't being able to build very detailed, very complicated models. The value was being able to run standard models very quickly. So being able to run 10,000 realistic versions of a geothermal system and seeing how all of those 10,000 perform, which ones fit the data we have the best, has been a real game changer. And so that ability, uncertainty quantification gives us, it means that we can produce forecasts that give a range of options. And that's key for making robust decisions. Instead of saying we're going to produce 20 megawatts, we can say, the P90 is that we are going to make 15. And that is a much better estimate for the decision makers. So the ability to set up models that are consistent with the geological conceptual models quickly, run them very quickly with our open source simulator YWERA, and then using uncertainty quantification mathematical tools, that's what gives us the ability to do this. So our approach at the moment is we still go through standard calibration techniques to get us in the ballpark of what we think how the geothermal system is behaving, and then we'll generate thousands of models by applying ranges to all of the parameters in the geothermal system. So we have, if you can build a geological model for well targeting, we can build a numerical model from that and then test out realistic ranges on all of those parameters that make up that model. And so what happens is once you put in ranges of parameters, and you can see some of these, for those, this is going to get a bit technical, sorry, but you know, we're looking at permeability ranges of 2 orders of magnitude easily in these. So you can look at very broad ranges of possible heterogeneity in the system. And you can see then we run those models forward, and all of them generate some representation of a geothermal system. And what you can see, this is from an example problem where we have a number of wells. This is a map looking down. Those are some structures, faults. And you can see every grey line is a different geothermal model. And so there's we're like 200 degrees variation across these different models. And the dots show the measured data from this system. So you can see by creating a big range of input parameters to these reservoir models, we get a big range of possible representations of the geothermal system. And then what we do is we use that data and the uncertainty on the data, which is really key. We're not just using the data, but the uncertainty on the data to tell us, well, which one of these thousands and thousands of models are a reasonable representation of the geothermal system. And that's what, in this case, and those are parameters you can set. You can say, how much do I trust different types of data? Here we're using downhole temperature, but the key thing with this method is we can use any data. So, you know, we're talking to Berkeley about how we can use the seismic data as well and to constrain this. We're already using resistivity to constrain this. It doesn't have to be, it can be any type of data at all. And then once you take the models that are the best representation of the true system, you can run through and you can do forecasts. And I just showed this in the production reinjection workshop. But you can do forecasts forward, and now you get those really important ranges on your forecast, saying this is our expected P50, but this is the worst case scenario, this is the best case scenario, given the range of possibilities. And this is the interesting case showing without drilling new wells or with drilling new wells, and you see what you would expect to see, that the uncertainty goes up when you're adding new wells to a system. So given that we've got this new ability to do uncertainty quantification using advanced modeling techniques, let's think about geothermal resource assessment. So the traditional method, which is older than I am, I turned 50 last year, this is over 50 years old, is a stored heat calculation or a heat in place calculation. It's a very simple method to calculate the energy that can be extracted. It's the kind of thing that I teach my first year master's students how to do this and answer this in their test problems. So we do Monte Carlo over a very limited number of parameters, and the important thing is we have something called the recovery factor. Now the recovery factor takes into account hundreds of different things, and it can be, how deep you drill your wells, what's going to happen to the recharge of the system, what type of wells you're drilling. All of those factors have to go into the recovery factor. It's very uncertain. No one knows what it should be because it's a fudge factor or a factor that takes into account so many different variables. This is fine as a first estimate, a rough first estimate, but we can do much better than this. This is 50-year-old technology. So the idea is that now that we can run reservoir models so quickly that we can run thousands of them, what we can do this at the very earliest stage. As soon as you can draw a conceptual model or build a geological model for drill targeting, we can run reservoir models of it. And we can run thousands of them. And we can test all of them and see which ones match the data. And the key point is, for a resource assessment for a greenfield system, we do uncertainty quantification, but we just have no production history data. So we're only using that early stage exploration data. But the important part about it is we're forecasting forward using models that respect all of the reservoir physics and the wellbore physics. And I'll talk about it and I'm putting an example of that too. So this is it. This is the new method. It's basically fast. We set up models very quickly, we run them very quickly, and we use some clever mathematical tools to choose which models fit the data we have the best. And that gives us uncertainty quantification. And what we're going to do is we're only going to use exploration data, and that gives us a method for resource assessment. So what does that, this is the example I just mentioned. We use the resistivity to infer a clay cap, and then we can choose all of the models which match the clay cap to some degree. This is obviously for a volcanic or high temperature system, but as I mentioned, we're going to work with all different types of data, seismicity, chemistry. We can use any data to choose the models. So this is a temperature plume, and so we expect to see clay forming at around 190 to 200 degrees. So we know that we should only choose geothermal models that produce temperature distributions that align with that. And in this case, we don't have any downhole data because no wells have been drilled, but you can see the same thing happens when this was all of the thousands of models. When we look at the ones that fit the clay cap, we end up with a much narrower band of models that we select going forward. And as I said, this can be any early drilling, so maybe you've got 1 or 2 wells. It can be geothermometers, we can do flows to surface features. We're looking at chemistry, and we're going to look at seismicity to bring into this too. And then what we do is we have an algorithm which is pretty simple that basically stress tests every single model. All of these red models, we then stress test them, seeing how much fluid or energy can we pull out of the system with realistic production and reinjection. And so that we loop around in an iterative way, adding more production and reinjection until we see a maximum amount of energy being taken from each of these thousands of versions of the system. And again, that only works because we can do this so fast, right? So we're running a forecast from a reservoir model that might have used to take 2-3 hours. We're doing it in 30 seconds. So we can do it iteratively, and we can do it on 10,000 computers in the cloud. So we've already done this on many systems in Indonesia, and which we've published at some conference papers, and there's going to be a journal paper out soon. And we're actively working with the Renewable Energy Ministry in Indonesia to look at using this method in a way to support their database of greenfield systems as a systematic way of providing realistic, robust estimates to the public. We've also done it in other locations as well, and that's in Colombia and also in Portugal. So this is the kind of results that you get out of those estimates. This one, the comparisons with the stored heat were fairly similar, and you can see, so each of these grey lines are forecasts, and we look at you can get the P90s, P10s for the total amount of power out. And so, as I said, every single one of those is a full-scale geothermal model run through to forecasting, including wellbore modelling for the production and reinjection. And just before I move on from that and finish, one of the things with the wellbore modelling we found that was in this case the stored heat gave pretty similar estimates to the simulation-based resource assessment. But one of the other projects we did, the results were very different. And that was because in the system we looked at, it was actually under-pressured because of a very deep water table. Now, there's no way to account for that in the stored heat calculation except by setting a very low recovery factor, which there's no reason to do if you weren't aware of that wellbore physics. And what we saw with this new simulation-based resource assessment was that we got a much more realistic estimate of what the resource availability was. So the key thing about this is we're not using necessarily more information than a stored heat calculation. We're just using it better and smarter and making sure that we're obeying the laws of reservoir physics. You know, we're looking at how the fluid actually flows and how the well bores perform as well. And now, as we expand on the data that we're going to be using, then we are going to be adding extra information into that, and you have the possibility of using a whole range of exploration data like it's being gathered here in Taiwan to essentially help build more robust estimates and de-risk development by having a more accurate representation of the resource. And so it's only possible as this is only new technology because of those advancements in being able to do reservoir simulations so quickly and so powerfully using cloud-based technology. And we now have several of our long-term clients and collaborators. These are key deliverables. So all of our new projects, we always offer this as a deliverable. And in our relationship with Contact Energy in New Zealand, and also clients in Indonesia and Australia, we deliver quarterly forecasts with uncertainty quantification included. So this is a standard deliverable. There's no reason not to do it. The technology is now available, and the value the value of having these robust forecasts is not to be underestimated. Thank you very much. Any questions?